Engine ignition. And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet. And Atlas TU has gone to closed loop control.
We have indication that cruise stage separation has been confirmed by the spacecraft.
MRO reports the electro radio is powered on, ready to receive signals from the lander.
We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface.
February 2021. The lander carrying the Perseverance rover has entered the Martian atmosphere. The suspense in the control room is almost unbearable. The team has no control over what will happen in the next few minutes.
We are starting the straighten up and fly right maneuver in preparation for parachute deploy.
MRO's reporting good telemetry log.
For the engineers from NASA and CNES, the French National Space Agency, this was what's referred to as the 7 minutes of terror. Perseverance had to touch down as gently as possible on the Red Planet.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 480 meters per second.
Perseverance was carrying a dozen sophisticated instruments, which would be used by one of the most ambitious space missions to search for traces of past life on Mars.
Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface.
Here the rover was less than 2 kilometers above the Martian surface. This was the last stage of the landing, and likely the riskiest.
The confirmation that the back shell has separated.
The ground station could only watch. Signals took 11 minutes to reach Earth. Either the maneuver had been successful or Perseverance had crashed.
The maneuver has started. About 20 meters off the surface. UHF is good. Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
That 7 minutes, I think, was the shortest and the longest 7 minutes of my life. For me, the really special moment is those few minutes after landing when we got the first picture of Mars.
All stations, stand by for the images.
Wow, my robot that was here 7 months ago, that's been in space this whole time, is on another planet.
Congratulations to the mission.
This image was among the first sent from the Martian surface. The Perseverance rover was apparently intact and fully operational. The robot was tasked with uncovering the secrets of the Red Planet. Perseverance was sent millions of miles from Earth to help answer a question as simple as it is exciting. Did life once exist on Mars? What would the rover discover in its first year of exploration? Mars has long fascinated astronomers. But it wasn't until the 19th century when Giovanni Schiaparelli discovered the supposed Martian canals that the question raised of intelligent life on our neighboring planet first emerged. The American astronomer Percival Lowell mapped these canals, mistaking them for artificial structures built to irrigate cities that had long since disappeared. The myth of the Martian was born.
Invaders from Mars.
Starting in the 1960s, probes were repeatedly sent to explore the Martian surface without success.
In
1976, the Viking mission ran 3 experiments looking for organic life on Mars. They found nothing, so they lost interest in Mars for 20 years.
Since then, several rovers have been sent to explore Martian soil. The Pathfinder probe, carrying the small Sojourner robot, was the first in 1996, followed by Spirit and Opportunity. The last 2 proved that water must once have flowed on Mars. Curiosity, the big brother to Perseverance, landed in 2012. Its mission was to find out whether water could once have facilitated the development of life on the red planet.
Curiosity went to Mars to establish its habitability. Was Mars habitable 3.5 billion years ago? We found that yes, it could have been habitable. It had the right ingredients. So then Perseverance takes it one step up, right? And it says, okay, well, if it was habitable, was there life on Mars?
Just like for Curiosity, NASA commissioned the Jet Propulsion Laboratory to build several prototypes for Perseverance, each with different sizes and different technological profiles.
Perseverance was built based on the idea of Curiosity. We took a lot of the systems that existed on Curiosity and used that as our baseline for Perseverance.
They may look very similar, but the internal mechanics signal a new generation of rovers. Sophisticated high-tech developments. Specialized cameras, spectrometers, lasers, ground-penetrating radar, an oxygen production instrument, and a robotic arm for coring and storing rock samples.
These are extremely complex robots. There are 200 to 300 scientists behind each vehicle.
It took 6 years to develop, build it, and launch it, and then another 7 months to land on Mars. It takes an incredible amount of time to design everything, build it, make it space-rated, test it, because we also have to test and demonstrate that it's going to work in that Martian environment.
Conditions on Mars are hostile to life. The biggest problem is the extreme temperatures, and Perseverance also had to generate its own energy.
The problem with using solar panels on Mars is that you're so much further away from the sun that you need a much bigger area to get the same energy as you would here on Earth. We sometimes have dust storms on Mars, and so that's often how rovers meet their demise on Mars. For Perseverance, we use a nuclear source which over time creates heat, and that heat is transformed into electricity.
This generator would ensure that the rover and its instruments could function on the Martian surface without disruption for years to come.
When we build missions like Perseverance, it's not just an American mission. So when we build this rover, yes, it's built here at the Jet Propulsion Lab, but pieces are built all over the United States, all over the world. And so the SuperCam instrument, for example, is a French instrument.
SuperCam acts as the eyes of Perseverance. One of its features is a powerful laser that vaporizes tiny rock particles to analyze their composition. This allows chemical particles to be identified within a radius of up to 10 meters in the plasma generated by the laser.
I developed it together with Roger Wiens from the Los Alamos National Lab in New Mexico. We were thinking about how to measure the chemical composition of Martian rocks and soil. I asked about his lab's capabilities, and he said, "We know how to make spectrometers and analyze light. What about you?" I told him in France, "We know lasers." So we divided the labor, and 20 years later, we had designed the SuperCam.
SuperCam uses a system of lasers and spectrometers. With this telescope, we can obtain extremely detailed images of the surface of Mars. You can see details of around 20 microns per pixel when the camera is close to the ground. This is the first SuperCam image. These instruments conduct precise chemical and mineral composition analyses and can even detect the presence of organic material.
Lanzarote. Millions of years of volcanic activity have shaped this unique landscape. These geographic properties make it the ideal training ground for space travel, including the exploration of Mars. The simulations help to train missions with robots and soon perhaps even with humans. Geologist Charles Frankel is an expert on Mars and has taken part in several simulations himself.
This volcanic landscape really resembles the Martian landscape. It's even aligned along a fault like the red planet. And the oxidization is red, like on Mars. At first, Mars and Earth were very similar because they had the same origin. At one time, there were rivers which fed the lakes, and there was a magnetic field, or a protective shield that stopped the atmosphere from being eroded by solar wind. But it changed drastically about 3.7 billion years ago. The magnetic field from the planet's core abruptly vanished. Mars was so small that its atmosphere dissipated into space. The red planet became a freezer. A sort of ice age suddenly took over, and it never recovered, turning it into the dead planet it is today.
Has Mars retained traces of its past? The scientists hope so. The mission begins. The teams from the French National Space Agency, or CNES, and NASA are adjusting to Martian time. The days there are longer than on Earth. Each Martian day, known as a sol, lasts around 24 hours and 40 minutes, so the clocks have to be synchronized.
Great, thank you.
The mission has started. We have a reference period of 3 years. If the rover fails before that, then we have also failed.
On board, dear. Hand over the next bag, you got about 9.5
Another thorough check to make sure all the instruments on board are working.
Our rover has an auto-nav system, so it can self-drive on the surface of Mars. Driving on Mars isn't that easy, right? We don't have a map, we don't have a phone that we can just say, hey, send me in that direction. So what the rover does is it takes pictures in front of it. It actually looks 5 meters ahead. And so that way it can actually drive from 200 to 300 meters a day autonomously. So it will drive itself. We can say, hey, at the end of the day, just drive in that direction for an hour and a half and we'll see you tomorrow. And it will do that.
There is a time delay in communicating with Perseverance. Although the signals travel at the speed of light, it takes them a number of minutes to reach the rover. A command from Control Center. Then, millions of kilometers away, Perseverance starts moving. At night, the rover remains stationary. It transmits the information collected during the day to Earth and receives a program with tasks to complete the next day.
Each point is assigned coordinates. So when we tell the rover to target a point, it knows exactly how to turn its head to fix on the point we want. Then it sets 5 points in that direction with the laser, with infrared, and the camera.
She was very quick to get everything done, and I suggest we release her.
First, we ran extensive tests for 3 to 4 months. We made sure the arm was working properly, if the wheels were okay, if the head turned correctly. Then we checked if SuperCam could fire its laser twice, then the green laser, then toward the sun, and not at the sun, but at the sky. We learned how to use our instrument.
SuperCam even captured a Martian solar eclipse for the first time, produced by the moon Phobos. Finally, operations could begin. The first job was to study the Martian soil. The rover landed on Jezero Crater, a huge depression created by a meteorite. NASA chose it from hundreds of other locations because it was the most likely place to find fossilized traces of past life.
We chose the Jezero site because it's a very old impact crater with traces of a delta. We have proof that a river once flowed into a lake there, because to have a delta, you need a river and a lake.
The crater is about 45 kilometers wide, with a lake several hundred meters deep, enclosed by a delta. The lake held about 5 cubic kilometers of water and a layer of sedimentary deposit 70 meters thick.
Above all, we wanted diversity. Rocks from the bottom of the lake, from around the sides, and from the delta. So we chose a site with all this diversity in a concentrated area.
Perseverance at work. The rover's cameras have already shown that the area consists of very different geological layers.
One day, the camera person pointed out a hill in the distance, and we said, let's take a photo and use it as a reference point. When we saw the incoming data, we said, that's fantastic, we're at the bottom of a lake. So we had our first results.
The photos were revealing, but virtual exploration of the crater provides limited insights. So the rover made its way to the delta. For its own safety, it moved extremely slowly.
In 200 days, we moved about 2.5 kilometers, so only a dozen or so meters each day.
Enough to work at leisure, but not enough to explore the huge Jezero Crater quickly. A little more speed was needed. Ingenuity, a small helicopter, was brought along precisely for such tasks.
Ingenuity is a technology demonstrator. There's 3 challenges to proving that your helicopter can function on Mars, right? Atmosphere is one of them. The atmosphere of Mars is 1% the density of Earth's. So very, very thin atmosphere. The other 2 aspects, though, is the temperature. It gets very cold, negative 90 degrees Celsius overnight. The third aspect that's different from Earth is the gravity. It's about 1/3 the gravity of Earth. The way we test that here at JPL is we have a chamber about 5-6 stories tall. And in that chamber, we were able to balance the atmosphere, the environment, the temperature, and the gravity of Mars here on Earth.
Ingenuity weighs just under 2 kilograms. Its 2 counter-rotating rotors turn 10 times faster than those of a conventional helicopter on Earth.
For me, one of the most difficult moments on Mars is the day that we dropped the helicopter from the belly of the rover, where it was attached, down to the surface of Mars. I was in charge of those activities, and it was, I can tell you, incredibly stressful to make sure that our little friend was on Mars carefully.
Popped 3 meters off the surface of Mars, hovered for 39 seconds, and then came back down. We had that first flight. There were 4 remaining to round out our 5 total in our 30 days. And thankfully, at the end of those 30 days, Ingenuity was still healthy. The Perseverance team and NASA decided there's value here in continuing to fly on Mars. Ingenuity can act as a scout. We can fly to a cliff wall. We can dive down into a cave, right? We can go to very high altitude and loiter or do a lawnmower pattern over a region of interest, for example. Ingenuity today is already providing reconnaissance for the Perseverance rover.
Sent ahead as a scout, Ingenuity sent high-resolution images to help Perseverance find its way to the Delta. On its 26th reconnaissance flight, Ingenuity even found the burst heat shield and parachute from the rover's landing. The route was clear. Now Perseverance could tackle its real mission, the search for traces of life on Mars.
We weren't looking for some macroscopic animal roaming around. That would have been easy. No, we were looking for traces of life that already existed on Earth at that time, and maybe on Mars. Primitive bacteria.
Michel Vizo is a veterinarian and works as a scientific consultant for the French space agency CNES. He is one of the world's leading experts in exobiology.
When we talk about extraterrestrial life, we focus on the simplest microbiological form, microbes. So if we find bacterial traces on Mars, we've found a new form of life. If we find a concrete trace of life, even fossilized, that is evidence of another life form in the universe. That's what we're looking for, even if it doesn't lead to Martians.
There was a period of 500 million or perhaps even 1 billion years when conditions on Mars were suitable for life. But was that enough for life to actually develop? I tend to think so, because chemical traces prove that 3.7 billion years ago, life emerged in Earth's oceans. I would like to believe that the same thing happened on Mars. And if life developed on Mars, where is it now?
Où est-elle aujourd'hui?
After a 5-kilometer journey, Perseverance finally reached the Jezero Crater Delta.
If the origins of life evolved from some prebiotic chemistry, then it most likely would have been in an environment of carbonates and clay minerals. So these are primarily what we're looking for.
We think that certain organisms living in very particular places on Earth today could also develop in certain microenvironments on Mars.
Purificación López García specializes in microorganisms that thrive in extreme environments. The hydrothermal Dalal area in northern Ethiopia is certainly one of the most impressive examples of a biosystem where life seems impossible. But despite extreme temperatures and acidity levels, single-celled organisms can be found in some areas.
At the edges of Dalal, there are ecosystems sustaining life, particularly archaea. These are unicellular microorganisms, like bacteria, particularly well adapted to very high temperatures of up to 120 degrees and extremely fluctuating pH levels. Studying these extramorphiles lets us better define conditions in which life could have appeared and persisted in extraterrestrial systems. If life emerged on Mars that could survive under such conditions, it could effectively exist in these systems as well, provided there was liquid water and an energy source.
Unlike the Earth, the Martian crust has never been reshaped by plate tectonics. This allows Perseverance to examine very old clay minerals. If there was once life on Mars, these minerals might still contain its components, like nitrogen or carbon.
To find intact organic molecules, it's best to dig a little deeper. And the rover's core can drill holes several centimeters beneath the surface to penetrate rock where they've been protected for millions or even billions of years.
Perseverance took its first sample of soil that might contain traces of organic material.
I would argue that that sample caching system is just as complex as the rest of the rover. It has to be able to take sample cores from the surface of Mars, process them, put them in the tube, and then pass that tube to another robotic arm inside the rover that then takes pictures, does some certain analyses of those samples, seals them because the samples are going to stay on Mars for a long time, and then it has the ability to deposit those sample caches on the surface of Mars.
We hope these samples will one day come back for lab analysis. To conduct a detailed sediment analysis, we need a laboratory with electron microscopes and high-resolution chemistry. That's not possible on a rover.
Perseverance will only store some of the tubes, not all of them. So rather than make one big pile with all the tubes and risk losing them all if the mission aborts, we leave a trail of scattered piles, like Hansel and Gretel leaving a trail of breadcrumbs.
They hope to eventually recover the samples from Mars and bring them to Earth for analysis. It's an ambitious project, especially because it's not yet clear exactly how this would work.
If you thought that collecting those samples and dropping them on the surface of Mars was already extraordinary and hard enough, eventually we're gonna wanna go bring those back. And so the teams here at the Jet Propulsion Lab and at NASA are already working on thinking as to how we might wanna do that.
That's the first time we're gonna launch something off of another planet. And then we have to bring it back home here to Earth and bring those samples back home safely and keep them contained. There are any number of challenges here that kind of dwarf anything we've done before.
The space flight system for the return mission should be ready in a few years. Researchers are already working on the new assignment.
These tubes will be recovered by a European-built rover, which will gather them with an arm, put them in a basket, and deliver them to a rocket, which shoots the container and its tubes into orbit around Mars.
This rocket will probably need its own lander. It will need to land very precisely near the tubes. It won't work if it lands 100 kilometers away.
The sample retrieval lander has a concept that we're working on right now, which allows the rocket that's going to take those samples from the surface of Mars to space to be thrown up in the air. We toss the rocket up in the air and then fire it. It's kind of like an air launch. And that's really the biggest advantage, is that we don't have to deal with any kind of erection system, right, to put the rocket in some kind of position that we want.
The rocket is almost 3 meters long and weighs 400 to 500 kilograms. You fire it in the air, the rocket ignites, and it's gone before it can come back down.
Once the orbiting sample canister, that OS, is up in Mars orbit, we've got to find it with the Earth Return Orbiter. Remember, we're looking for something that's kind of basketball sized. That's pretty difficult, right? It's not a very bright thing. It's not very big. And we're going to have to find it from, tens to hundreds of kilometers away.
Putting a small white balloon into orbit around Mars and catching it with an orbiter? Not easy.
So we start by looking for the other parts of the rocket that have gotten with it, that are bigger. The upper stage of the rocket has a radio on board with a beacon that will kind of scream at us every now and then, telling us where it is.
The captured container gets loaded into a space capsule, which returns to Earth 6 months later.
If all goes to plan, Martian rocks will one day be transported to Earth. It is crucial to ensure the samples are not contaminated by organic molecules brought by Perseverance from Earth. Though the risk is low, the consequences would be devastating.
The first space explorers in the 1960s remembered one thing: their own predecessors' lack of caution. The spread of disease following the exploration of the New World is a dark chapter in human history, and that contagion went both ways. Biological contamination of a Martian life form would be irreparable. The same is true in reverse. What would happen if an astronaut was contaminated by an unknown Martian species? What would you do with them? Could they be brought back to Earth? Or leave them there forever? Should they be brought back to Earth, but put in confinement for the rest of their lives? This is the stuff of science fiction movies.
A huge number of questions remain unanswered, but the ultimate goal remains. One day, humans will fly to Mars. But how can they survive there and return to Earth?
So for Perseverance, in addition to establish whether there has been life on Mars in the past, one of the other goals is to prepare for the eventual coming of humans on Mars. And so we have a few instruments on board that allow us to prepare for that. There's the META instrument, which is a weather station. It allows us to understand weather patterns on Mars, not just wind, but also dust, pressure. There's a ground penetrating radar called RIMFAX that allows us to understand the structure of the ground below us. If we're ever going to build anything on Mars, understanding the Martian regolith is really important.
Jean-François Clairvoy is a French engineer and astronaut. He has been involved with 3 NASA space missions and knows how important remote projects are before the first humans travel to Mars.
We need to be able to remotely fly to and return from Mars before doing it with humans. That's why this test mission with Perseverance is important for deciding if we conduct a human flight to Mars. But to do that, you need to be able to mine as many local resources as possible for eating, drinking, breathing, and supplying the return trip. So everything doesn't need to be sent from Earth.
It is impossible to land on Mars carrying 30 tons of material, including oxygen, and stay for several months. But Perseverance is already helping to solve the problem.
Perseverance is not just studying Martian geology, it's preparing Mars for humans. The rover is carrying a small box the size of a car battery called MOXIE. It weighs 17 kilograms and converts the Martian atmosphere into breathable air.
There is less than 1% as much air on the surface of Mars, but that air is 95% made up of carbon dioxide. So within each carbon dioxide molecule is an oxygen molecule combined with carbon. So the job of MOXIE is to take those apart.
MOXIE sucks in carbon dioxide from the Martian atmosphere and passes it through an electrolyzer, which separates the oxygen and releases the carbon monoxide. Then, the oxygen atoms combine to form breathable oxygen molecules that can be inhaled.
Now, you or I would take 20 to 30 grams an hour just to live and to go about our business. So far, MOXIE has run 8 times on Mars and it made a little more than 50 grams of oxygen, which means it would keep us alive for a couple of hours. We hope with a larger version of MOXIE to make all that oxygen in situ to support a human mission on Mars.
Humans will discover a lot more than robots once they land on site. Artificial intelligence is quite sophisticated, but it only does what it's programmed to do. A robot will never shout, "Oh, look."
Oh, regarde.
I long for the day when humans, with robots and cutting-edge scientific tools, will be able to answer the question of extraterrestrial life.
The question of alien worlds and extraterrestrial life haunts philosophers, theologians, and now scientists. Are we alone? There are two distinctly terrifying possibilities. One is the fear of being completely alone. If we are, the responsibility is terrifying. If life on Earth vanished tomorrow, there would never be life in the universe again. But the possibility that we are not alone is also scary. If we are not alone, then we are perhaps not the most beautiful or the most intelligent. That would bruise our egos. For some philosophies and some religions, that's difficult to accept.
Pour certaines religions, c'est assez difficile de l'admettre.
Our dream is to go to Mars one day, and I hope it will come true. That's the challenge of the 21st century. But this dream cannot be used to justify the idea that what we do to the Earth doesn't matter, because there's a planet B. No, there's only one Earth, and we need to take care of it. It's just about exploring another planet, and that's hard enough to do.
I don't know who named it Perseverance, but I think that's one of the most important qualities of a great researcher. Perseverance could be used to name basically any scientific program.
Perseverance will continue its search for life on Mars. The lone robot is not just exploring. It will also help make one of humanity's greatest dreams come true: taking people to Mars.
Birds in the clouds, all I do is dream and facing the stars. All of them are blinking, and I